welcome to millimeter wave communication for 5G and beyond. So, last time we have talked about the equalizer part at the receiver for the MIMO case, for the single case, single meaning it is a CISO case, but multiple antenna. Now, we will be talking more on the. So, today we will be covering the more on the what happens when I go to the MIMO case, how the equalizer will be based on. Okay. So, things that we will be covering are the following. So, I am just redrawing the RX side. Okay. So, now you have some multiple antenna, probably I will draw, let me draw a few more. Okay. And this is a NR number of antennas are present here. Okay. And so, what we said last time that whatever channel comes into picture here, if it is assume I am just sending from one antenna H 1. So, what will happen? Then it is nothing but you can create your own equalizer. So, one of the equalizer technique is like if I want to use MRC, it can also be LMMSC, whatever, there is no choice, it is up to you, but it is some sort of an equalizer. So, let us generalize that concept. So, you can have equalizer here, you can have an equalizer here, right. So, this is what we have explained it last time, and once the equalizer is built, then what you have to do, you have to combine them together to get the result. Again, it depends on the data model, but usually if it is a single input CISO case, this is what the system. So, this will be your equalized data. So, this would be more of a I would say R is equal to, if I would have sent X sense, I would say X n plus some noise. So, this is what my data is, this is what my data model is, right. So, this is for the single antenna case, single antenna in the sense single data case, not the single antenna, of course, it is multi antenna system, but single data case. Now, think when you have the MIMO case, just like your TX, you just add them up. Here also I will do a very similar approach. Now, this is one part of the story. Now, when it is a MIMO, which means that it is no longer just one channel, right, one channel will be coming into picture, because there may be multiple threads or data, this kind of data will come into picture, it is not just one data. Now, when you have this kind of scenario, this is now it can be, I am just generalizing it here in this case. So, W 1, this would be some W 2, and this would be some W n, whatever. So, if there are n number of equalizer or R n NR number of equalizer, so this can be the case. Now, what happens when I have MIMO? So, exactly when I have the MIMO, I cannot just simply take multiple things, right, because here if you look at here only, it is possible when the sent data is just one, it is easy to do it, right. But when I have the whole thing in more of a in a MIMO system. So, what will happen is that I have to first take some of the effect out from the channel in the MIMO context. So, in the case of MIMO, the similar thing will be happening here, but there is a catch. So, I still have NR number of antennas, because number of antenna may not change at the receiver, just like your transmitter, it is just the number of feeds or the digital feeds that will be changed, right. So, that is the in the case of MIMO. So, this is in the case of MIMO beamforming. Now, I am at the receiver side. Okay. This is at that stage kind of things. So, here as I said, I cannot just use MRC, because MRC won't work, because here number of digital data feeds itself are more. So, I can have probably S1 here, or in fact instead of S1 I have written it is X1, right, because that may be your digital data feed. So, that can be M. Then it goes from the TX side, this is the case, right. So, this is from the TX side, and then it goes to the beamforming in between, and then it goes to the RX side. So, this is my RX side. Okay. Now, here what I do a slightly different way. So, here I may have the LNA and all. So, let me not draw the LNA part, because this is more of an implicit part. So, what I am trying to say is that this NR I will send it through some sort of a RF matrix kind of multiplier. Okay. So, this I will send it here, this I will send it here, this I will send it here. Okay. And you can have your own dimension of the data. So, let us say I am making a dimension NR cross, you can have say M1, you can have M1 also. Now, M1 can be NR equivalent, I mean it is up to you how do you want to make. Now, this I call it WRF, which I did it in the TX side also, there was a WRF which was more of a beamforming part. Here also I do a similar setup combining. So, what happens? So, basically first you do a combine the data such that you optimize your SNR or optimize some of the cost function, then you go for a detection. That is the point. In the same case of single thing, it was not so prominent, though it was implicit. For example, the output of what is the output of equalizer? This is not the exact output of my equalizer, because there is more to it. If you look at the way it is, it was y vector, and it was multiplied by some sort of an equalizer vector. Okay. Then it is not exactly coming out to be an x n, rather it will be some sort of a x n plus some value will be there, maybe some constant or something, plus v dash n, because this equalizer will have some additive and then some adjustable things are there. Now, as it is single, this was not an important thing, because I can always divide this whole things. So, you can say whatever. So, let us call it some s constant. So, you can always divide it and make this fellow, this I call it a new V n. So, it is as if like x n plus V n, sorry, it is as if like x n plus V n. So, this factor was there. Now, this for single case it was very easy to handle, but when you go for a multiple data stream, then you can't simply take out that particular thing. So, here WRF I call it R part, just to indicate that this is at the receiver side. So, this was more of a combining part. Okay. So, you have a multiple data stream and then you combine them with some matrix. So, I would say this is some sort of a matrix. Okay. Now, moment that goes into a matrix, now this was my R vector. Okay. Now, what happens? So, at the end I was receiving y vector and I was getting R vector from there. How I get the R vector? I multiply the y vector with this matrix. Now, this is purely in the RF domain. Why is it in the RF domain? Because in the single case also I have shown a part of this can be RF, because the equalizer I can just put it as a phase shifter. You have seen it, right, in some of the earlier classes. This equalizer, it has a amplitude part, it has a phase part. The amplitude part I push it to the LNA and phase part I just implement it. Similar concept I will put it here as well. Okay. That it is a combined thing. So, it will include that itself will include LNA, phase shifter and all these things. So, this is some sort of an RF matrix, the completely it is in the RF domain. Now, once I get this R, you can notice that I have not written Rn, okay, because I have not digitized it. So, this was more, now we will explain it more how this can be estimated or this can be found out. Now, this R you can, this is a vector. Now, from here you can have you can have your normal ADs, you can have your demodulator and ADC, you can have your ADC here, and then you can create actual R1n, and similarly I will get it R M2n. If there are M1 numbers, sorry, this would be M1, this sort of things I can get it. So, earlier what is the difference between the earlier single case and multiple case, multiple antenna case? Earlier this WRF was nothing but one vector, okay, but now it is no longer just one vector, rather it will be multiple level of such vector. Okay. So, in the earlier case what happens? Let us do some more surgery into the exact structure of your WRF. If it is a single data stream, what would have been the case? In the single data stream, I was multiplying this y vector with the equalizer vector, right. So, either you can say y bar or so w star vector. This was the case, right, earlier, that is how the case. So, which means that I have one, for example, I have one w star vector here, and then I multiply with my y vector. It is not a single case. From here I was getting that r, and then I digitize it, I get Rn. This is what the case, right. Now, because now it is a MIMO case, what will happen? It is no longer just one W will be acting. Why? In the TX, if you remember how the feeds are there, if you look at in the TX side, there is an adder, right. There was an adder here. So, which means that each and every data from one antenna is already having multiple, multiple digital data thread. So, if I just use one W, I cannot write Rn is equal to what? Which data will come? Is it first data, second data, third data? You do not know, right? Because there are x1 to xm number of data are present, right. So, which data will be coming here? Because every data is there, right. Every antenna is transmitting weighted sum of everything, right. So, that means it will be some summation of x1 to xm will be there. That means, from one thread, if I just use one equalizer, and this Rn will be some weighted sum of x1 to xm plus a noise, I cannot reconstruct x1 to xm, because it is one observation and I have multiple input data. So, I cannot handle that. So, what I do? I create multiple such vectors, equalizer, and that is the fundamental principle of equalizer. That means, instead of W, I will say W1 dash, this will be W2 dash, then it will be W3 dash, and so on and so forth. I can have, if this is m, I can also have m number of such things, no hurry or no harm in that, or you can have your own. It should be at least more than this m, more or equal to m, because if it is less, then again it will be more data compared to my observation. So, the idea here is that how do I create more and more different sets of equalizer, so that instead of just R, I will get R1, instead of R, I will get Rmn. So, now this whole thing becomes a vector when I go for a matrix thing. So, that is the basic fundamental idea. So, I hope you get my point here. So, if it is CISO to MIMO, the transition is CISO to MIMO, the transition is that I cannot use just one equalizer vector, because one equalizer vector will always give you an output which is a linear combination of all your input data x1 to x, because if you look at the antennas, all antenna will have x1 to xm, right. If had it been CISO, what is the difference? This x1, it will this will not be x1, right, because the same x is fed to all the antenna. So, in that case, this is one equalizer is fine, right. Okay, but when it is multiple things, what will happen? One equalizer and the multiplied by y will always give you a single R, which is which is a linear combinations of all my xn. That is precisely going to happen, right, because this has everything. So, obviously, whatever I decode or whatever I do, that also contain everything. So, which means that I need more observations for my data decoding. Suppose I have 5 input vectors, say let us say I am sending 5 data stream. So, can I just have one R1? Not possible, right, because it from one output I will have, and that contains all x1 to x5. So, it is not possible to decode. So, I need at least 5 number of minimum observation to get my x1 and x2. So, which means that I need some sort of a different linear combination of x1. So, that is the reason I have multiple such equalizer coming. So, as a whole, if I put it as a whole, I can call it some sort of a matrix. Suppose if this length is nr and I have say m1 number of such things. So, this is more of a m1 cross nr matrix I can think of. So, that is precisely this WRF is. Okay. So, if it is a CISO case, this WRF is just a vector equalizer, but moment it is a MIMO case, this WRF is no longer a vector, it is a set of vectors, because one vector multiplied by y, it will always give you one observation. Obviously, vector multiplied by another vector, if it is inner product, give me one observation. Now, in that observation itself, I have m number of independent unknown variable. So, one observation versus multiple inputs. So, I cannot decode such kind of things, right. So, obviously, I have to increase my observation. So, what is the best way to increase my observation? The best way to increase my observation is that instead of this WRA being one vector, consider it as a matrix, that is all, just like this fundamental principle. So, that means, I will create multiple such W such that I get variation in my observation. Okay. Moment I get a variation in the observation, what does it mean? It means that I will now have m1 number of observation, from there I have to get back my m number of input variable. So, this is the fundamental principle. So, in summary, if I go back to my diagram, in summary, so what is my data model now coming up? Now the question is that how this WRF will be implemented. Now, if you look at, it is like as if like I have parallel number of such W's. So, how did you implement one W? It is ln again multiplied by your phase shifters, right. So, nr number of LNA adjustment multiplied by phase shifter. So, you have m such parallel things coming into picture. So, if I just summarize, or if not summarize, if I just kind of brief about what exactly this implementation would be. So, 1 W 1 star multiplied by y observation. What was the result? This was antenna, this was the antenna, and this was the antennas, right. So, this was implemented as an LNA multiplied by a phase shifter. This whole thing is your W1 star, right. Now, after that what we do? I add them up. So, this is still inside my RF domain, and then I go to the digital part. So, then you can put an demodulator and then ADC, and you get by digital data stream. This is the part. Now, what happens when I have multiple such thing? This such boxes will be repeated m times. If the dimension of this matrix is m1, so I will have m1 number of such boxes. Okay. Similar thing. So, how the data line? So, this line will be fed here and this line will be fed here. Okay. So, now again there will be LNA, again there is a phase shifter, again there is an LNA, again there is a phase shifter, and you have again adder. Now, this is again in the RF domain. This after that what will happen? You have your demodulator, ADC converter and all these things, and finally, I get my digital data. Now, here I do not get the digital data, be very careful here. So, in between there is a, in between each and every line will go through demodulator, then ADC, because I and Q you will have. So, this becomes a complex number. So, this is the case, here also the same thing, you have multiplier, you have an ADC, you have an ADC, and that gives you RM. So, that is all it is. So, this is the RF to digital converter part, the output side is digital. This is precisely what happens, okay? And that's the point. Now, I am still not done. Okay. Now, what I said that each and individual R1, each and individual R1 will be what? Will be a function of, it is a linear function of your actual data plus a noise. So, this part is there. Okay. Now, when it is a linear function, why it is a linear function? Because everything is a linear system, why it becomes suddenly a nonlinear equation? It will not be. So, it is a some, you know, some combination of x 1 to x m. Here also it will be some combination, so I will say some function here, but it is a linear function, some combination of this is what is going to happen, right. So, now this whole thing would be my, you know, would be my data. So, now plus some noise. So, if it is V 1, I will have V m 1 and this is my noise part. So, ultimately this part is there always, because that is the resultant part which is coming out even after multiply an equalizer, because equalizer will have, you know, residual components and all these things like some multiplication factor and those kind of things, right. So, those will be anyway there, you cannot take it off there. So, all these components will be present there. So, basically the individual R n will be a linear function of my x 1 to x m system. So, if it is a linear function, so how do you visualize this R? Okay. So, this is very important, how do you visualize this R? Now, I can visualize this R as like this. If R 1, what is that? I said it is a linear function of x 1 to x m, obviously, because that is the resultant of my equalizer multiplication. Okay. So, that means I can say some, you know, some a 1 of x 1 plus, you know, a m of x m, that is the linear function, plus V 1. Now, I really need not to know what exactly my a 1 and a m will be there, because it will be automatically coming up if I know the channel. Obviously, if I know each and everything, a 1 and a m, everything will be known. I will explain that part. Now, what is the R m or m 1? Let us generalize it. This will be some, you know, a m 1. Okay, let me put a different notation here. A dash, sorry, a 1 here. This would be a m 1 x 1 this will be automatically popping up. You really do not have to, not this one, you really do not have to worry how exactly this a 1, and I will explain it. What is this linear funda here? So, this will be V m 1 and okay. Now, as a whole I can think of it, now this is a vector, right. So, I can call it R vector. What is its dimension? M 1 cross 1. So, that is the dimension that R comes. What is this one? If it is a linear combination, so obviously this whole thing I can think of it as a matrix A, okay, and a vector x plus a vector phi, right. So, what is this A matrix? A matrix, individual row of a matrix is like this, whatever a 1, a m, the last row is a m m to a m m 1. So, those kind of things, right. So, this is the A matrix. Now, how do you get the A matrix? It is easy to get. I mean, it is not something that you have to estimate, because that is the effect of my channel, all this WRF estimation, those kind of thing. But finally, this is what will be coming up in your data at the end of this data part, at the end of my RF extraction part. Okay. Now, this RF extraction part, when I do that, this is what my digital data comes, but I am still not done from my detection perspective. Now, let us come to the point How, what is this A funda? What is this? Now, let us go back to my data model. So, what is my data model? Data model is that R vector is nothing but, let me not draw 2, R vector is nothing but WRF at the receiver side, and then you have this Y vector plus W, not plus W, this is what is coming. Now, what is this Y? This Y is nothing but WRF into R multiplied by that whole channel matrix that we have talked about, right. That was your NR cross NT, that channel model. Then you have this WRF T, that is the transmit side beamforming vector and beamforming matrix we have talked about, and then WBB baseband side, and finally your X vector, X or S vector, whatever we have decided, plus a noise. Let me not consider the noise part currently, because noise is anyway implicit in this case, right, plus anyway whatever your noise part, that is not it's not my important thing, because I can always take this fellow off and I call it this whole thing WRF multiplied by this B, some resultant matrix. So, I just always keep that fellow separate. So, which means that that A matrix I was talking, right, it is impact of everything, that gives you the A matrix plus the noise. Now, if I know this, if I know this, if I know this, and if I know this, I can get A, no big deal, right. So, that means given all these 4 matrices so far, these are the transmit matrices, these are the transmitter side, this is the channel part, this is the not, I should not say the whole 3 things are transmitted side, these 2 are transmitted side, and this is my channel part. Now, if I know my channel, if I know my WRFT, WBBT, and if of course, WRFR is also known to me, because I am the one who is designing it. So, if all these 4 matrices are known, obviously, A is known to me. So, it is not so difficult to find out A. Okay. Now, we will see whether this A will be really required or not, we will see that, because there is no point in finding out A, because you know all the value of A, right. So, that is not a big deal. So, you know all the A. Okay. So, that means given, I just make a small comment, that means given WBBT, WRF at the T side, and H WRF R side, all 3 things are known, A. So, A is not a big issue for us. Okay. So, now we will see in the next class that is that what my story ends. I mean, is it where my story ends? Do I really need to A? Do I really need to know A? Okay. Actually, it is not required to know A, but what is my goal? My goal is to get back my X. That is my data, but that is what I transmitted it, right. So, that is my goal. I think if I am not wrong, I could have used a different notation in my earlier one. So, probably this was S bar, but that is okay, as long as you understand. That was the transmitted vector, and then WBB, and this was the digital picoder side, this was the beamforming part, and that is the channel. So, 3 things here, right. So, what is my ultimate intention? Ultimate intention is to, let me put a different notation, so that it will not ultimate intention to get back my S, because that is my information data, okay. But I am still not done, I am just proceeding step by step. So, in the next class what I do, I will now go for detecting my S part. Okay. So, with this I end the session here, and in next class we will be detecting the last part of my beamforming ones. So, in conclusion, we have kind of completed the and the reference will be same as what we have. Okay.